Alright, so welcome to my lecture on Chapter 8 of Chaos Theory. This chapter covers bifurcations in two-dimensional phase space. Okay, so like we said in one dimensions, we have certain types of one-dimensional bifurcations like saddle node, transcritical, and pitchforks. So the normal forms for these are given by we have x dot is equal to mu plus x squared. It's a saddle node, and this transcritical, which will be x dot is equal to mu x plus x squared. And here transcritical, remember that one of the fixed points just changes stability but is never like destroyed. Okay, so this is going to be something like this, right? And then we have pitchfork bifurcations. Remember, there's two types of pitchfork. There's subcritical and supercritical. Okay, so the supercritical example, we have we're going to have x dot is equal to x minus x cubed, and then subcritical, x dot is equal to mu x plus x cubed. So the super and subcritical in these cases are uniquely determined by the sign of the x cubed term. So whether or not it's a stabilizing or destabilizing term. In the supercritical case, it's a stabilizing term because it has negative slope. So I'm running out of space here, but for negative x cubed, we're going to get something that looks like this when we have three fixed points. And so the x cubed term causes the fixed points on the branches to be stable, whereas in the subcritical case, it's the opposite. So the x cubed term is destabilizing, and we have something that looks like this. Okay. And then recall, as we change the values of mu, these fixed points collide in and basically envelop the fixed point of the origin. Okay, so turns out in two-dimensional phase space we have all of these bifurcations, and they're like, it's really easy to extend them to two-dimensional systems. So let me show you how that's done. Okay, so for the saddle node, this is our one-dimensional case here, and then in two dimensions, the normal form for this, call it normal form, but essentially I'm going to change it to x dot is equal to mu plus x squared, and then y dot is equal to negative y. So this is a totally uncoupled system, right? And so it's kind of like a useless little trick, but it kind of gives us a geometric understanding of what these bifurcations look like. So if we draw out our two-dimensional phase space here, what happens is on the x-axis we have exactly this same process that's occurring in one dimension. So we have a stable and an unstable fixed point on the x-axis that collide together. Notice that these are fixed points because y is also 0 on the x-axis. And then, but two-dimensionally, we have an exponential decay to the x-axis, right? Y will always exponentially decay down to the x-axis, and so this is going to look something like this. Okay, and as you can probably guess, okay, so on the x-axis we can determine the regions of flow like we can do in one dimensions. Okay, so the direction of flow here, well, I did that wrong. Direction of flow here, here, and here. And then the outer curves that are like non-zero y values are basically going to mimic that behavior in the x direction, and they're just going to exponentially decay in y. And so we get these shapes, and we should expect that this stable fixed point is now a stable node, and the unstable fixed point is actually a saddle. Okay, and it turns out that's precisely what we do have. And if we wanted to prove this, all we would need to do is take the linearization of this system. Okay, so essentially the Jacobian, and then look at the eigenvalues for each of these fixed points. Okay, so moving on to the transcritical case, it's actually, I'm not going to go into it. It's the same thing as what I've just described here. The stable fixed points become stable nodes, and the unstable fixed points become saddles. But I guess we could go through it real quick. So let's actually do the linearization on this one and show like why they are saddles or not. Okay, so I'm going to set up a system x dot is equal to mu x plus x squared, y dot is equal to minus y. And now I'm going to factor this equation in x dot. So we have x times mu plus x here. Okay, and now I can see that, well, I'll keep the y dot, I guess. So I can see that the fixed points occur precisely at x is equal to 0 and then minus mu, and y is equal to 0. Okay, and so now I'm simply going to evaluate the Jacobian at these two fixed points. Okay, so I'm going to evaluate the Jacobian at 0, 0 and at 0 minus mu. All right, so let's find the Jacobian of the system. So remember that the Jacobian is just going to be the matrix given by taking this first function, partial differentiating with respect to x. So we get mu plus 2x here. And this entry is the x dot derivative with respect to y, which is just 0. The system's uncoupled. 0 is on the off diagonal of the Jacobian, and then a negative 1 here. Okay. So if you don't understand how I did this, you should probably review chapter 5 and chapter 6. Okay. And notice that these zeros in the off diagonal tells us that the system is completely uncoupled. So these differential equations are basically independent of each other. There's nothing really interesting going on in the dynamics between x and y. Okay, so now let's evaluate this, the determinant and the trace of this matrix. So I'm going to do it over here. Okay, so all right, so the determinant of this matrix is going to be simply negative mu plus 2x, and then the trace is going to be mu minus 1 plus 2x. And now if we evaluate at these two fixed points here, so the determinant at 0, 0 is precisely minus mu, and the trace at 0, 0 is going to be mu minus 1. Okay, so actually we have something interesting going on here. Okay, so notice how my critical point for mu is, so if we go back to the system, the bifurcation occurs at what value of mu, right? Well, precisely at mu equals 0. Okay, and at mu equals 0, this determinant is going to change from positive to negative. Okay, and remember that when the determinant is positive, we get nodes. When the determinant is negative, we get saddles. So if mu is any positive number here, then essentially, if mu is positive, this implies that we have a saddle. And then when mu becomes negative, saddle at the origin, right? This is where we're evaluating. So saddle at 0, 0. And then when mu becomes negative, we are going to have a well, let's check here. This trace will be negative, right? Mu is negative, so mu minus 1 has to be negative. And so we're going to have negative trace and positive determinant. So that will give us a stable node. 0, 0. Okay, and you can repeat the analysis for the other fixed point at 0 minus mu, but you're going to get kind of the opposite effect here, okay? And so what's happening is that the origin is changing from a saddle to a stable node, and it's basically exchanging its stability with the other fixed point. And this is exactly analogous to the one-dimensional case when we have a parabola sliding along and the origin changes, it exchanges stability with the non-trivial fixed point, okay? All right, so the last case we have is pitchfork bifurcations. We have supercritical and subcritical. And again, I'm not going to go into these because the argument is the exact same. We're going to have, for stable fixed points, they're going to work out to be stable nodes. And unstable fixed points, we're going to end up having saddles. Okay, and this is pretty much how it's going to go. Yeah, I'm interested to find out, you know, like what type of fixed points, or what type of bifurcations involve unstable nodes, right? Because if you have an unstable node, it's difficult for it to bifurcate because you can never have like a stable saddle for it to exchange with. So this is an interesting question. Maybe some of y'all in the comments can let me know your thoughts about like what type of bifurcations occur with an unstable node, okay? But again, for supercritical and subcritical, we're going to have, I can just draw you a picture, but I'm not going to go into the analysis. So just real quick, pitchfork. We're going to have something that looks like this. Maybe, you know, we have a system with these fixed points. This would be a supercritical, okay? And so essentially, we're going to have behavior that something like this, and then we're going to have nodes coming in here, node here, and then node here and here. Okay, and so essentially, these two stable nodes are going to collide with the unstable saddle and cause it to become a stable node. Okay, and they're moving along actually the manifold of the saddle. Okay, so they're moving along this one-dimensional space as the bifurcation occurs. Even though it's some more complicated trajectory in what I've drawn here, the basic behavior is the same. We have the fixed points, we have the stable node, we have the saddles colliding with stable nodes along the one-dimensional subspace of our two-dimensional system, and this is just analogous to a one-dimensional bifurcation. And so, even in more complicated examples of these one-dimensional bifurcations, there's like this topological equivalence to like an uncoupled system, simply because along the trajectory where the bifurcations occur, we have interesting behavior, and then orthogonal to the direction of the bifurcations, we're going to have like almost a decoupled, locally decoupled system. Okay. All right. That's all I wanted to say about these one-dimensional kind of extensions. Now, there's some other interesting cases that we could go into, and turns out there's other types of bifurcations that occur in 2D space that don't happen in one-dimensional space. Okay, so that's what I'm going to talk about now. And these are called, one of these are called hope bifurcations. Okay. So before we go into these, I want to kind of discuss the one-dimensional bifurcations that I covered earlier. If we look at the trace and determinant graph, okay? So if you look at the determinant, or no, sorry, not the trace and determinant, the eigenvalues of the Jacobian. So all the systems with a one-dimensional bifurcation, if we look at their eigenvalues in the complex plane, So in the examples I just gave, we have two negative eigenvalues, and then essentially one of these eigenvalues is crossing over 0 and becoming positive. And remember that if you have two negative real eigenvalues, you have a stable node. And then if you have like opposite sign eigenvalues, you're going to have a saddle. And so in all of these cases, we have one of the eigenvalues is changing sign, but they're exclusively real. Okay. But notice that eigenvalues can also be complex, and we could have like spirals, local spirals. And so this is a different type of bifurcation, where essentially we have a complex conjugate pair of eigenvalues, and these are actually crossing the imaginary axis, like so. Okay. And so when these cross the imaginary axis, you can imagine that locally the fixed point will change stability from a stable spiral to an unstable spiral. Okay. But there's something interesting that happens around the fixed point. So it turns out that in this process of changing from a stable to an unstable spiral, a limit cycle can be born from the system. Okay, so this is what we call a hope bifurcation. Is essentially we start with a stable spiral. This is actually a supercritical version of a hope bifurcation. We start with a stable spiral, and where our eigenvalues have negative real part, and then these cross the imaginary axis, and the spiral becomes unstable. However, a locally stable limit cycle is born around the fixed point. Okay, so the fixed point becomes unstable, but this stable spiral kind of grows. This stable limit cycle grows out of it. Okay, so let me draw the limit cycle kind of darker so you can see it better. Okay, and so the idea is that this stable fixed point, the way I think about it, is the stable fixed point almost like grows into a stable limit cycle, and what's left behind is this vacuum of this unstable fixed point. Obviously that's not mathematical, but this is how I think about it. And now we also have a subcritical. Now in a subcritical hope bifurcation, we still start with a stable spiral, but there's some sort of unstable limit cycle around it. Okay, so we start with a stable spiral and an unstable limit cycle around it, and that unstable limit cycle kind of shrinks and swallows the stable fixed point. So it becomes an unstable spiral. Okay. All right. Now, one important thing to note is that in both of these cases, if we just look at the local, the local picture of the fixed point itself, evaluating the Jacobian, we're gonna see that we go from a stable to an unstable spiral in both cases, the supercritical case and the subcritical case. We have a change from a stable spiral to an unstable spiral, and so it's more difficult to tell exactly which of these is happening without like more technical analysis. And like the author of this book gives some references, but then he also says, you should numerically integrate it and see. There's also examples where it's possible to kind of gain inference. For example, like if I convert the system into polar coordinates, which is a good idea if you're like dealing with spirals and limit cycles. If I convert the system to polar coordinates and I observe that R is like strictly increasing, then I can rule out the existence of a stable limit cycle. Okay. Or yeah, for example, if I use some of the techniques of the previous chapters to rule out the existence of a closed orbit in this state of the system, then I could prove that it's a subcritical Hopf bifurcation. Or similarly, I could prove, using a trapping region, I could prove the existence of a stable limit cycle, and then I could know that it was a supercritical bifurcation. But this is a lot easier said than done, because in a lot of these cases you have complicated systems, and trapping regions or like proving the existence of limit cycles is a pretty tough thing to do. So oftentimes mathematicians, according to the author, tend to use numerical analysis, numerical integration of the differential equations to kind of get a local view of what's happening. Okay. Now, let's just look at an example of these Hopf bifurcations and try to come up with a reason why this stable limit cycle is necessary. Okay. So, if we look at R dot, let me just use an example from the book. Okay, so an example from the book, we're going to have R dot is equal to mu r minus r cubed. Theta dot is equal to omega plus br squared, where mu, omega, and b are all parameters of our system. But we're really going to focus on mu, is going to be the parameter that we're going to study here. So, as we know here, this is exactly the normal form of a supercritical pitchfork bifurcation in the radial direction. Okay, and so as we can see in the radial direction, it's evident exactly why we're going to get a stable spiral. Okay, so in the radial direction, we're going to have originally something that looks like this, and then as we increase mu past 0, I can draw it in a different color. This is mu negative. And then as soon as we make mu positive, we're going to have something that dips below, comes out, and then through like this. Bad drawing, but okay, so this is mu positive. Okay. All right, and so as we can see here, this is going to be a stable fixed point, and the origin becomes unstable. Okay, so in the case where mu is less than 0, the origin is stable, so we have a stable spiral. Okay, and then when mu becomes greater than 0, all of a sudden the origin changes stability to unstable in the radial direction, but we still have this angular clockwise flow given by omega plus br squared. So the direction of flow is governed by this equation, and specifically near the origin it's governed by omega. Okay, so that's going to determine if our spiral is clockwise or counterclockwise. But this r term here, the r dot term, like is going to determine if we have a stable or an unstable spiral. Okay, specifically if the fixed point at 0 is unstable in the radial direction, then we're going to have an unstable spiral, for obvious reasons. And then notice how this fixed point doesn't just change, doesn't just flip a switch and go from stable to unstable. Instead, it bifurcates, right? We have the supercritical bifurcation where the two fixed points are basically born and split apart, and the origin becomes unstable. And so this stable fixed point on the right here, that's born out of the bifurcation, this is going to correspond to precisely, notice how r dot is equal to 0. So that's just going to be a circular limit cycle surrounding the unstable spiral. And this indeed will be stable. Okay. So the best way to kind of understand these, the Hopf bifurcations, It's just looking at like a radial cross-section of your system and recognizing that we're really just looking at bifurcations in the radial direction. And so the fact that a stable limit cycle grows out of this makes a lot of sense when you think about like one-dimensional bifurcations in the radial direction, okay? And the subcritical thing is the exact same picture, okay? It's just in reverse, okay? So the same exact reasoning can be applied here if you just look at a subcritical pitchfork bifurcation in the radial direction, all right? Okay, so that covers the Hopf bifurcations. There's also one other kind of Hopf bifurcation, and this is a special one, and I think it's called degenerate, okay? And the degenerate Hopf bifurcation essentially occurs when, usually in like conservative systems or something, when we go from stable spiral, and then the spiral becomes unstable, but that transitionary point, right at the bifurcation, we get a bunch of periodic orbits that are non-isolated, so like a bunch of centers, and then it goes to an unstable spiral. And notice that in the cases where we have a stable spiral going to an unstable spiral, this is the case where you're not surrounded by any limit cycle anywhere. You're just going from a stable spiral to an unstable spiral. And the transition point of this is precisely a bunch of nonlinear centers surrounding your fixed point. So if you have a system that has like it's a conservative system or some sort of reversible system, and you can prove the existence, using methods of the previous chapters, you can prove the existence of nonlinear centers, then it's possible you have a degenerate Hopf bifurcation if you're going from a stable to an unstable spiral, okay? So yeah, that's what I wanted to cover about Hopf bifurcations. Now there's also global bifurcations of cycles. All right, so global bifurcations of cycles occur not at a fixed point, but actually with limit cycles, as the name implies. So, for example, if I look at the radial direction of a two-dimensional system, and I essentially say I have something that looks like this. So say I have like a quintic function, and then I change some parameter, and this dips below the r-axis here, and I get a saddle node bifurcation that's not at the origin. Okay, so say I get something that looks like this. All right, so in this saddle node bifurcation in the radial direction, what's happening in a two-dimensional phase space is that two-dimensionally we have two limit cycles being born. Okay, so I have a stable limit cycle and then an unstable limit cycle, and they're being born from a half-stable limit cycle, precisely when this parabola dips and hits the r-axis. Okay, so this is the type of bifurcation, I believe. Yeah, so for analyzing the direction of these limit cycles, we would just have to look at the sign of theta dot, okay? But the idea is essentially the same as the saddle node bifurcation in the radial direction, and this time we have the creation or birth of limit cycles instead of fixed points. I think that's pretty straightforward if you think about kind of what's happening here, and then you just extend it to a two-dimensional phase space. I think it makes sense. For example, if you want like an example of this, you could look at like r dot is equal to mu r minus r cubed plus r to the fifth or something like this. And then there would be a critical value of mu where you'd actually get like a saddle node bifurcation that wasn't at the origin. And this is precisely when you're going to have a bifurcation of cycles. Specifically, it's called a saddle node bifurcation of cycles, I'm pretty sure. And then there's one other thing that we could have. So the last phenomenon is called an infinite period bifurcation. And so previously, with the Hopf bifurcations and the global bifurcations of cycles, we really just look in the radial direction, and all of our analysis comes from breaking the system into polar coordinates and then just viewing all of our skills from the one-dimensional examples in the radial direction. This one, we actually need to use knowledge of theta dot, and you're going to have a bifurcation essentially in theta dot instead of r dot. Now remember, theta, because we're in polar coordinates, is 2 pi periodic, so we actually have flow in a circle. Okay, if we just look at theta dot for a second. So say we analyze the value of theta dot, and then all of a sudden, say we have theta dot is equal to mu plus sine theta. Okay. So when I bring mu above or below 1, all of a sudden theta dot has no roots. Okay. And specifically when I lower mu and bring it to 1, our sine wave, which I'll just draw for you here, so our sine wave we essentially shift the value of mu, and when mu intersects that sine wave, we're going to have a bifurcation that occurs on the circle, on the flow in the circle. Okay, and for simplicity, it worked fine what I just wrote, but for simplicity, I'm going to do mu minus sine theta. Okay, and so essentially, when these two lines, mu and sine theta, intersect, we're going to get fixed points. Okay, so here at the angle of pi halves, which occurs right here, we're going to get a saddle node bifurcation, and so on the circle, I'm essentially going to get a fixed point, a half stable fixed point that splits into 2, right? And I think if you look at the sign here, it should be, well, let's quickly determine the stability of these. So if you look at theta dot prime, derivative with respect to theta, we're just going to get negative cosine theta. And so it's negative for the smaller angle, which means it's stable at the smaller angle. And it's, here's theta. And it's unstable for the larger angle. Okay. All right, perfect. So this is precisely what would happen if we were just, went back to chapter 3 or 4, whatever, and looked at flows on the circle, is we'd get something like this. All right, now let's extend this for 2 dimensions. Well, essentially, imagine that this is a limit cycle in 2-dimensional space, and what we could have is we could have some sort of bifurcation where fixed points are born on a limit cycle. Okay, so this actually extends beautifully to 2-dimensional phase space, because in a trivial example where r and mu are decoupled, we're going to have, like, say we have r dot is equal to 1 x squared minus 1. I'm sorry, 1 minus x squared. Okay. So if you have r dot is equal to 1 minus r squared, and theta dot is equal to mu minus sine theta, essentially what we can do is observe that there's a stable limit cycle that exists precisely at r equals 1. Okay, So at r equals 1, we have a stable limit cycle here. And then the origin is unstable. And I'm getting this just from looking at r and r dot here, the one-dimensional flow on the line. Then we have something that looks like this, and we have a stable and an unstable fixed point here. Now, this is kind of confusing because yeah, I think this is a confusing example because of what happens at the origin. So let me just quickly change it. I'll just do r minus r squared, but the logic should be the same. I'm just going to make it so that we have a stable point at the or unstable spiral at the origin. Okay, so before, when I had 1 minus r squared in the radial direction, that's like really kind of undefined at the origin because we would just have, yeah, I'm not sure how that would work at all. Again, another thing for the comments, I guess. So, but going back to this example, so if r dot is equal to r minus r squared, if we draw the phase portrait for this, we're going to have an unstable fixed point at the origin, stable and non-trivial value of r, and that's going to correspond in two-dimensional space to an unstable spiral at the origin, and then a stable limit cycle at r equals 1. And then to determine the direction of this, let's just say mu starts off as something large. So let's just say we start off with mu being, I'll draw sine theta, and we could start off with mu being some very large positive number, okay, out here, mu. Then essentially, all of my flow, no matter what the value of theta is going to be counterclockwise, okay? And also, one thing that I'll note is that since I'm subtracting sine theta, the magnitude of theta dot is going to be smallest at pi halves, and it's going to be largest at 3 pi halves, okay? So at pi halves, precisely along the positive y-axis here, we're going to have slower movement, and then on the negative y-axis, we're going to have fast movement. So I'll write that fast and slow here, okay? And hopefully you understand where this is coming from. This is coming from the analysis of theta dot and looking where the magnitude of theta dot is greatest and smallest, okay? And so now, with this in mind, what I'm going to do is look at what happens when mu bifurcates, okay? So when I lower mu and intersect this sine wave here, all of a sudden, I'm going to get like very, very slow movement along the positive y-axis, okay? So it's going to be super hard for it to rotate through this section, and almost all of the time the system's going to spend near theta equals pi over 2. And then finally, once I bifurcate, I'm essentially going to get a fixed point being born, like here. I'm going to get a stable fixed point and an unstable fixed point on this limit cycle, precisely like how I drew before, right? And so I'm going to have a fixed point born at pi over 2, and it's going to split into 2. And then essentially what I'm going to have is these rays that are invariant, okay? So this fixed point is going to actually become a stable node, and then I believe the other fixed point will become a saddle, okay? But the idea is that along these rays of these values of theta here, theta stops changing, so the system stops rotating at all. So once I hit this ray, I'm basically confined to it forever, and so other trajectories will asymptotically approach these rays. And so now we might get something that looks like this. Might get something that looks like this, and then it kind of approaches this here and here. And so the behavior along the limit cycle, which is now no longer a limit cycle, it's now a manifold of this saddle and of this stable node, okay? So the limit cycle becomes the manifold of these fixed points, of this saddle and this stable node. But essentially, along what was once the limit cycle, we're going to have the exact behavior that we've looked at previously with flow in the circle, and then in the region surrounding it, these two fixed points, similar to how we looked at like in the trivial one-dimensional cases, this fixed point is going to become a stable node, the other fixed point is going to become a saddle, and then our origin is just going to remain an unstable spiral. And so now when I say like stable node, saddle, and unstable spiral, these are like local topological phenomena, right? So when I linearize the system and look at its eigenvalues of that linearization, that's a very much a local phenomena because it's linearized, okay? And so because of that, we can expect the behavior of these to be topologically equivalent to like saddle, spiral, and stable node. But in like further out, if once we kind of move far away from them, we can't really expect that type of behavior. But in this kind of example, knowing the local kind of what the portrait looks like locally, we can kind of piece together a mapping of what the whole flow on the whole system might look like. And then of course we can verify that using some sort of numerical integration. Okay, so that's all that I wanted to talk about for the global bifurcations. Now, of course, you know, I haven't been doing many examples or problems from the book, but I think, you know, understanding the fundamentals is a lot more important than people think, because all of the more complicated examples kind of flow from like a lot of algebra and just knowing the fundamentals. Okay. All right. So let's see here. Yes. So one last thing that I forgot to mention. Okay. So there's one last bifurcation that I should mention. It's called a homoclinic bifurcation. And essentially what happens with the homoclinic bifurcation is we have like a saddle, okay? And then we have like another limit cycle. So say I have some sort of supercritical Hopf bifurcation that occurs around this non-trivial fixed point here. So say I have a system that looks like this, and then I have like a local saddle like this, okay? Okay, and so what happens is, as I grow this limit cycle can kind of expand, and then essentially it will envelop the unstable manifold of the saddle, okay? So the saddle, it's going to have some sort of manifold like this, and then say my limit cycle's here, and yes, flows that look like this, okay? Then essentially, as this limit cycle grows and grows, eventually the limit cycle is going to morph into the saddle here and become a homoclinic orbit, okay, which is essentially the unstable manifold of the saddle connects in to the stable manifold of the saddle, okay? And just a reminder, if you forget, saddle, if you take the eigenvalues of a saddle and then you take the eigenvectors, those will give you the stable and the unstable manifold. So the unstable manifold for the positive eigenvalue, the stable manifold for the negative eigenvalue. And essentially, along those eigendirections here, there's going to be one stable direction where you have exponential decay corresponding to your negative eigenvalue, and then one direction where you have exponential growth corresponding to the positive eigenvalue. And so what happens is that a limit cycle out here grows and then basically morphs in to this to the manifold of the saddle and does something like this, and then as it continues to grow, it just gets destroyed, okay? And so the key to identifying these types of bifurcations, they're a bit more harder to identify, but you look at what actually happens along these manifolds. So here, this manifold might do something like this and kind of asymptotically approach the limit cycle, okay? But in other cases, once the limit cycle grows, it becomes a homoclinic orbit, the saddle, and then it grows further and just breaks apart basically, and then this unstable manifold might move in the opposite direction. And so by looking at the direction of the manifolds of the saddle, that's how you identify if you have a homoclinic bifurcation occurring, okay? Right. Now, the final thing we'll mention for this chapter is Poincare maps, okay? So Poincare map is basically a way to identify or prove the existence of some sort of closed orbit. And it's very useful in like cobwebbing diagrams, okay? So, as a simple example of a Poincare map, if we look at some sort of periodic solution, so say we're looking at flow on a cylinder, okay? So this would be the phase space for something that's periodic in one variable but not in the other, okay? So say we have like a theta dot and an r dot, okay? Essentially, yeah, or wait, I think it's, okay, yeah. So, not theta dot and r dot, like a theta and a y, okay? So we have some y coordinate and then some periodic coordinate theta, okay? Then essentially, if we look at the flow in this circle, we could have some limit cycles on the circle. We could have these types of limit cycles, which are called librations. Okay, so this is a libration. Or you could have a rotation, which is a limit cycle that essentially starts at one point, goes around, and then returns back to the same initial starting point, okay? And then essentially what a Poincare map does is it's trying to prove the existence of some sort of periodic orbit, okay? Or like a stable limit cycle. And so the way that it does it is that basically you take a lower dimensional subspace of your system. So in this case, I'm going to take a vertical line. Okay, and then you look at, and this vertical line is on the edge of the cylinder. Hopefully that is clear. You look at how your trajectories, they might start on this line somewhere, and then they might go around the circle here. They might end up here, okay? So after a full kind of 2 pi radians have elapsed, you look at where they end up on this line, okay? And so basically, you take your subspace and you start out with y, and then you take p of y, which is the Poincare mapping of y, and that's basically y at 2 pi, okay? In this example, okay? And so, and we just look at this as like basically a mapping, a discrete mapping. And so if I start with y, and then I have p of y, I want to look at wherever I start on this line, I go through the rotation, where do I end up? And that's going to be a function of where I started. Okay, so that's precisely the Poincare mapping. And if we notice here, whenever I have p of y equal to y, so if I ever intersect this line of slope 1, then that's precisely going to be a limit cycle, okay? Because of the fact that if y equals p of y, then I'm going to end where I started, and then the motion will just repeat itself, okay? So that's what we're doing, is we're looking for intersections with this line with slope 1. Okay, so the problem is the way to actually solve for P of y is you might say you have like a y dot is equal to a function of y and theta. You have theta dot is equal to some other function of y and theta. Okay. Solving for P of y is somewhat tricky, and so a lot of times you need to do it numerically. So basically you integrate the system of differential equations through an angle of 2 pi, and you look at where the system ends up on that Poincare section, okay? And so say I have some random system, I numerically integrate, okay, I start at y equals, I start here, I integrate the system, and I get back here, whatever, okay? And now I'm gonna plot that input and output and form a graph called a Poincare map. And basically, if I have something like this, based on this map, I can identify like where my orbits, my periodic solutions are going to be. They're precisely intersections with this line. And now Poincare mappings are very, very useful, and oftentimes there's ways to prove that that this intersection exists without even using numerical integration. For example, if I can show that at some point, like say y naught, I have P of y that's greater than y naught, okay? So P of y naught greater than y naught. And then at some later point y1, I have P of y1 is less than y1. Then I can basically, and I show that the Poincare mapping is continuous, which basically means that my differential equations depend continuously on the initial data they're given, okay? Which is sufficient, as long as f and g are sufficiently smooth, they will. Then essentially, I can say that since P of y is a continuous function, I started above this line and now I ended below it, I'm definitely going to intersect it somewhere. So I can prove the existence of a periodic solution. Now, the last thing about these Poincare mappings is identifying the stability, okay? So the stability is actually governed by the slope of P of y, okay? So specifically, at the fixed point, so let P of y star equal y star. So this is like a fixed point of the Poincare map. Then we just look at if the absolute value of P prime of y star, okay? So take the derivative of the Poincare map with respect to y. If this magnitude is less than 1, then we have a stable orbit, okay? And if the magnitude is greater than 1, we have an unstable orbit, okay? Now let me explain why this is. Basically, it's because if I start at y star and then I perturb the system by some nu, okay? Now, let's say I start at some slight perturbation away from the periodic solution, and now I take the Poincare mapping of this. Well, since the Poincare mapping is continuous, I can Taylor expand, and I'm essentially going to get P of y star plus P prime of y star nu plus higher order terms, okay? And so the sign of this, locally, the sign of this is going to determine the stability, because P of y star is just y star, okay? And then we have plus P prime of y star here. And so the question is, does P of y star plus nu actually cause the perturbation to decay or to expand? Well, this is exactly given by the sign, or not the sign, but the magnitude of P prime of y, okay? Because if P prime of y has magnitude less than 1, then each time I iterate the Poincare mapping, I'm going to end up with y star plus some number less than 1 in magnitude times nu. And so the perturbation is going to decay geometrically, okay? And now obviously, on the other hand, if P prime of y star is greater than 1 in magnitude, then we have an unstable periodic solution, So the fixed point of the point care map is unstable. Now, the important part about this is that the sign doesn't actually matter. So sometimes people think this sign is what matters, but no, that's a common mistake, and the sign of p of y doesn't matter. It's actually the magnitude that counts, okay? Quick note on point care maps, we could have higher order systems where, say we have like a 3-dimensional space, which we're going to get to next chapter, and so we have flows in like 3 space, okay? And now I can take a point care map that's a 2-dimensional subspace, so it's always an n-1 dimensional subspace. So here's my point care section here, and then essentially I'm looking at how these trajectories flow through the point care map, okay? So obviously I want the system to be somewhat periodic, okay? Or, you know, I need to know for certain that if a trajectory intersects P at one time, after some later time it will come back to the point care section again. And then I like kind of look at how it intersects, right? So let's say I start here, why not? Or like, I could just say x naught, and then I let time elapse over some period tau, and then I look at, you know, p of x naught here. And so I have a point care map in higher dimensional space. And the only thing that, you know, is required is that trajectories have to flow through the point care map. So they can't flow like across it, right? They need to be so the trajectories need to be flowing through the point care map, not across it. And yeah, that's pretty much it. The last, I guess, system that I could mention is the flow on a torus, okay? So we talked about a cylinder, we've talked about a plane. The other possibility is a torus, where essentially we have 2 periodic variables that we're analyzing. We have like a 1 value of theta and a different value of theta here. Okay, and so here our subspace is actually going to be a torus. Okay, so something like this. And we're just going to look at flows along this torus. So it might look something like this, and then come around here, and loop around. So this is a bit more complicated, right? However, the torus can actually be expressed by something called a magic square, where basically, since theta 1 and theta 2 are periodic, I can just take their range, in which they're uniquely valued, okay? And then, essentially, I can represent my trajectories as flows along this square, where anytime I hit an edge of the square, I'm just going to zip over to the other opposite adjacent side. And so if I zip over here, you know, trajectories are going to look something like this. So hopefully that makes sense. It's just basically this magic wall here. Once I intersect it, I'm basically going to come out the other side, the opposite side at the exact same height. Okay? And that corresponds to basically saying that theta at 2 pi is the same thing as theta at 0. So I can just teleport my trajectory back by 2 pi. All right? Now, there's interesting things about flows on a torus. So specifically, if we just analyze the trajectories like along the magic rectangle, then essentially we can have the existence of limit cycles, okay? And specifically, we can have a global bifurcation of a limit cycle, say something like this. And this would appear as essentially some sort of line on our magic rectangle. Okay, so essentially, let's say I have theta 1 dot is equal to mu minus sine theta 1, and theta 2 dot is equal to mu minus sine theta 2. In this simple example, when the system bifurcates, essentially we're going to get that theta 1. Wait, hold on. Actually, I think it's like, yeah. So that wasn't the best example. I'm sorry. It's where these examples come from is essentially the best way to analyze the magic rectangle is to look at, or sometimes the best way to analyze it is to look at the phase difference. So theta 1 minus theta 2 dot. You can call this phi, okay? And basically, if there's a bifurcation in phi, okay, then yeah, is equal to phi dot. So let's say I analyze theta 1 dot minus theta 2 dot, which is the phase difference, or I guess the derivative of the phase difference. The phase difference is just theta 1 minus theta 2. Okay, phase difference. So I apologize, I got off track there for a second, but if you look at the phase difference and say we have a bifurcation in this phase difference, okay? So let's say that, phi dot ideally is just a function of phi, and we get some bifurcation that occurs here. Then what will happen is the system will become phase locked. So theta 1 minus theta 2 will be a constant. And so that is going to correspond to these vertical solutions in the magic rectangle, which are basically periodic or quasi-periodic orbits, depending on if the phase difference is a rational multiple of 2 pi. But the idea is that in this phase locked system, I'm going to have, say this is locally like mu minus x squared. Okay, then essentially, once I get my mu minus b squared, once I bifurcate, I'm going to have these stable lines and unstable lines in the magic rectangle, and then the flow in the magic rectangle is essentially going to approach these lines, like so. And now, as I kind of remove the fixed points of phi here, these lines are getting closer and closer together, and then basically the fixed points will coalesce and annihilate each other, and I'll just get quasi-periodic or periodic flow in the magic rectangle. Okay. So the point that I'm making here is that the way you analyze flow in a torus, you use the magic rectangle because it's locally linear behavior, and then essentially you can look at, use previous analysis of the local linearizations for any fixed points that might occur in the magic rectangle. But then another powerful tool is using the phase difference, okay, and looking for fixed points in the derivative of the phase difference, because if you're able to do that, then it's like reducing it down to a one-dimensional system. But you have to remember that if this is a fixed point in the phase difference, then it's not going to be a fixed point on the magic square. It's actually just going to be a line, which is corresponding to a stable periodic solution with this constant phase difference. Okay, so I hope that this helped. I would definitely kind of try to look more into the torus example, and I think I probably could have covered that a little bit better. The book does a great job. But anyways, I hope this was helpful, and have a great day.